Thank you very much, and thanks to the organization for letting me speak here. There's only 7 slides separating you from leisure, but you haven't seen them yet. So, deciding the discreteness of SL2 over local fields, I opted to give an overview of a couple of results I obtained in recent years, and also results by my students. So, local fields come in 3 flavors: the real numbers, the complex numbers, and then the non-archimedean local fields. So, I'll start with some history for SL2R, so for Fuchsian groups. So in the 70s and 80s, Rosenberger and Persitsky and also some others classified the discrete two-generated subgroups of PSL2R. So the reason there's 70s and 80s there is there was a series of papers where there were some little gaps and they needed to be fixed over time. It's very easy in this business to miss a case. Nowadays, in the results I will present later, we had the help of computer packages, and then you can see you have missed something, but otherwise it's harder. In 1983, Riley had an algorithm to decide whether a finally generated subgroup of PSL2R is discrete. These groups are so-called geometrically finite, and basically what he does is he runs through all sequences of words, and either he finds 2 that give you a 4th domain that give you a fundamental domain, or he finds 2 words that together violate the discreteness condition. Gilman and Maskett, they have a more efficient algorithm to decide whether a two-generated subgroup of PSL2R is discrete, but they have the restriction to 2 generated, whereas Riley was for any finitely generated. So Zhang analyzed these 2 algorithms. So one of them is polynomial with respect to the maximum word length, so the length of the maximal word used, and Riley's one is exponential because basically it has to go through all the options. Then in 2014, Bettina, Kirschmer, and Charles solved the constructive membership problem for 2 generated discrete and free subgroups of SL2R, and then later Kirschmer and Rutger solved this for 2 generated discrete, so not necessarily free. So Eamon and I, together with Matthew Conder, we had a student, PhD student, Ari Markowitz, who just finished, and Ari has the following result. So if you take a finite subset, so like not 2 generated, now any finite generation of SL2R or PSL2R, he produces an algorithm that decides whether or not X generates a discrete group. And the way he does that is by sort of replacement with Nielsen moves. It's quite an involved, clever technique that he came up with all by himself, by the way. And sort of, you can see here sort of visually what happens. We start with the Cayley graph is embedded in the Poincaré disk, and it doesn't necessarily have a nice representation. It has self-intersections and stuff. And then Ari has a technique where if your group is discrete and free, for example, you can do successive replacements to get rid of this self-intersection to get like a more familiar Cayley graph. And if he can't do that, then he will like find an elliptic or things like that. So his algorithm is basically for discrete and torsion free. But then with Selberg's lemma, you could find a finite index subgroup, although that is in practice not always that handy because the number of generators can explode quite badly. But the algorithm for discrete and torsion free is very quick, actually. I should also mention that once he has this, he can find this fundamental domain. He can also solve the constructive membership problem. So constructive membership problem, if you don't know, it's if you have a finally generated subgroup in another group, and I give you an element in the bigger group, you want to know whether it's in this subgroup, and if yes, you want to write a word. And the way you do it is you take a point, you send it out, and then you bring it back by looking at a generator that brings it closer to that V until you can't anymore, and if you have found the inverse, it's in, otherwise it's not. Okay? Then I started about 2 generator classification of SL2R subgroups, so then you can ask, Gaven asked this question a few years ago, can you also do this in a non-archimedean case? So this is joint work with Conder, but this is Matthew Conder. Some of you might know Marston Conder, this is his son, Matthew Conder. So we can basically produce a list, and we also have an algorithm, so you can, if you have rational matrices, you can put it in the computer. It's programmed in Magma, not by me, because I only ever opened Magma once and then closed it again. But Matthew programmed all this, so you can give it matrices, and these are the isomorphism types. There's one little thing we can't do. If the residue field is characteristic P greater than 5, P 2, 3, or 5, and if it's not a p-adic numbers but an extension thereof, we can't do it. This has to do with the fact that you need to compare fixed point sets of elements with fixed point sets of their powers, which for general groups are different. But in this p-adic setting, you have the happy coincidence that if you're not in the situation I just described, then these fixed point sets are the same, and then you can do like an analysis. These groups that appear here, this is because the finite subgroups of PSL2K are either cyclic dihedral A4, S4, or A5. And so the technique is a lot of case-by-case analysis, and either you use a sort of a Klein combination theorem, which is a generalization of the ping-pong lemma, or you create an infinite vertex stabilizer. And if you have an infinite vertex stabilizer, you cannot be discrete. And in this case that I describe here, we couldn't do either. So that's in terms of classification. There's some interesting application of this classification because, for instance, you can see which are the two generated lattices, and I actually could also have allowed positive characteristic here. You can only get this if you have two generated lattices in there. In the beginning, I tried to prove there were none, but then I found an old paper by Alex Lubotsky and Thomas Weigel where they had this example. And once I knew this one example, it was actually very easy. And also interestingly, you can also get an algorithm to decide if a two-generated subgroup of SL2K is dense. How do you do that? In two steps. First, you check whether your group is Zariski dense or not. And Zariski dense, if you're not Zariski dense, then you're elementary. And that means you're going to either fix a point or you're going to like swap 2 points. These are conditions which are very easily checked on your generators. If you're going to fix a point, the two generators better fix it. So you can do a couple of algorithmic checks to see whether you're Zariski dense or not. If you're not, then you're also definitely not dense. If you are Zariski dense, then there's only a couple of options. Either you are discrete, but this I can check now. I can check whether I'm discrete or not. If I'm not, I have already checked whether I fix a point. So if I'm not discrete and I don't do this, then I must be dense. So this gives you a nice algorithm to check that. Then Ari also has a result for automorphism groups of trees. Of course, you need to also make some computational assumptions. When I talked about SL2R, you need to either put rational matrices in or you need to assume you can compute with real numbers. Here, in the general setting of a tree, you need to say like, well, I can compute paths, etc. Of course, the application that we will have in mind is the application of the SL2 over non-archimedean local field, where then the corresponding tree will be the Brouhat-Hitz tree. So you will have the action on the Brouhat-Hitz tree. So you take a simplicial tree, take a finite subset, which generates a group G. Then there's an algorithm that, given this X, you will output either a free basis or you will have an elliptic element in there. So you can detect whether something is this discrete and torsion free, then it will produce a free basis. And the principle is the same as in the SL2R case. You do successive Nielsen transformations to make, look, for instance, here I started with a red axis and a blue axis, and they have some overlap. And then you do these transformations. Either you find they're elliptic, or in this case, now the blue axis and the red axis are separated, two hyperbolic axes. Ping pong immediately tells you this is discrete and free group. So that's kind of the, and here Ari uses like lexicographic ordering, and it's all fairly involved, but in the end the result is quite clean. And then, so the last case I haven't talked about is the complex case, aptly named complex case. And that's, I mean, Gaven is the world expert on this, and I sort of learned from him, and we had a joint student, Alex Elzenaar, who's very strong. So here, there's no hope at this stage of a complete classification, although there has been classification based on Ian Eagle's program for groups generated by two parabolics, and we are working on extending this to two elliptic generators. Here, only under certain conditions can you guarantee that it's discrete and free. And so if you have two parabolics, for example, parabolics are translations. You can rescale, so you can represent them by 1, 1, 0, 1, 1, 0, z, 1 with Möbius transformations, and this z is a complex parameter. And what you see in this picture here is it will be discrete and free if you're out on the outside of the eye. Then it will be discrete and free. But the boundary of this eye is a very complicated fractal. So it's very difficult algorithmically to know whether you're in the eye or not. And some steps towards knowing that is like we proved the theorem that identifies regions around these are so-called pleating rays. That's called king series theory. And then you identify these regions, and if your point is in one of these regions, then it's out on the outside of the eye. And we have also in recent years, so this is generated by two parabolics. You can ask, what if you do it with two elliptics? Then you have other so-called Rayleigh slices, and you can do similar things. And one of the applications we have in mind would be nullification of all the finitely many generated arithmetic triangle groups in BSL2C. I know this is way too fast, but the main message you have to take away here is that it's much more complicated, but on the other hand, maybe also much more interesting than the other cases. And you're not far from your leisure now. Thank you.